Hey, this is Mr. S, and today we're going over 2.2, what is matter and what happens when it undergoes change. So the two concepts we're going over is that matter consists of elements and compounds, which in turn are made up of atoms, ions, or molecules. And 2.2b, whenever matter undergoes a physical or chemical change, no atoms are created or destroyed, the law of conservation of matter. So this might be review for some of you, but it's good to review these essential scientific points. Okay, so matter consists of elements and compounds. And take a look at this list because these are the chemical elements that I expect you to know or understand and could be important for this book. So matter is anything that has mass and takes up space. It can exist in the three physical states, solid, liquid, and gas, and two chemical forms, elemental and compounds. An element such as gold or mercury is a type of matter with a unique set of properties that cannot be broken down into simpler substances by chemical means. Chemists refer to each element with unique symbols such as C for carbon and A for gold. AU for gold, excuse me. They have arranged the known elements based on their chemical behavior and a chart known as the periodic table. And most of you have seen that in chemistry. But most matter consists of compounds, which are combinations or two or more of different elements held together in a fixed proportion. So for example, water is a compound H2O containing hydrogen and oxygen, and sodium chloride contains the elements sodium and chlorine. That's table salt. If you took table salt, one of them is a metal and the other one is a toxic gas. You put them together and you get table salt. It's amazing. All right. So elements and compounds are made of atoms, molecules, and ions, which you see here. And protons and neutrons are what form in the nucleus. But atoms are the smallest unit of matter. And elements are made of atoms, okay? So they're essentially the same thing. Elements are just different types of atoms. And incredibly small. 3 million atoms run across the period on this sentence. And in the period there would be 3 million atoms. Atoms are made of subatomic particles. So protons, neutrons with no charge, and electrons which have a negative charge. And the protons again and neutrons again are in the nucleus of the atom, and the electrons are these tiny little things that whiz all around the atom. So the atomic number, what you see on the periodic table, is the number of protons and neutrons in the nucleus. All right, and then we have isotopes, molecules, and ions. So isotopes are an atom with a higher level of neutrons in the nucleus, and that's what causes radioactivity. So for example, that should say carbon usually has 6 neutrons and 6 protons in the nucleus, C12. But it can also take the form of carbon-13 and carbon-14. And these are important things to think about because this is what radioactivity is when there's a huge amount of neutrons and protons in the nucleus, and when they get shooted off, it creates a huge excess of energy. And so molecules are 2 or more atoms. And then finally we have ions, which are charged molecules or atoms. And here we have caffeine, which is one of my favorite molecules. And so the thing about ions that are really important and why I bring that up is that they're important for measuring a substance's acidity. So a measure of the comparative amounts of hydrogen, H+ ions, and hydroxide ions, OH-. So what do these make when you put together? What do you think? H2O. All right. So, and I will draw that here. So H+ and OH-. Okay? And these are what determine how acidic or alkaline. So if there's a high amount of H+, it's very acidic, and it goes to be less than 7 for acidic. And if there's a huge amount of OH-, it becomes very basic. So like soaps are very basic, baking soda, things like that, they're alkaline. Okay? So remember that acidic things are less than 7 on the pH scale. Okay, so now we're going to quickly talk about organic compounds, because they are the chemicals that make up all life. So plastic, table sugar, vitamins, aspirin, penicillin, and most of the chemicals in your body are called organic compounds, which mean they have at least 2 carbon atoms combined with 2 atoms of one or more other elements. And so example is glucose, which most plants and animals break down in their cells to obtain energy and to give us donuts. So larger and more complex organic compounds, called polymers or macromolecules, form when a large number of simple organic molecules are linked together by chemical bonds, somewhat like real cars linked, train cars linked in a freight train. So there are 4 types of macromolecules we're going to review: complex carbohydrates, and proteins, nucleic acids, and lipids. And so these are what all life is made of. So I want you to take notes of this and make sure that you know each of the major building blocks of organic molecules. So here we have complex carbohydrates. They're made of the glucose that we saw here. When you start stringing them together, you get these complex carbs. And so these are what plants make to store sugars and what give us life. And plants also use that glucose to make the cell walls or cellulose. So that's another complex carbohydrate. There's many different types. Then you have proteins, which are super important in your body. You learned last year. They're linked amino acids. They help store energy. They're important for the immune system, hormones that turn off various bodily functions, hair, skin, muscle, and tendons. All right? And some proteins store energy, some are for the immune system and chemical messenger. So yeah, they're just super important, and they speed up certain reactions. You have nucleic acids, which are made up of nucleotides, which are phosphates and sugars, and one of the 4 nucleotide bases, which represent a G, C, or T. So you should remember this from last year too. And these are DNA and RNA. And so these help build proteins. These are the information texts that tell your body and all of life which proteins to be made. So the different molecules of DNA in the millions of species found on Earth are like vast and diverse genetic libraries. Each species is a unique book in that library. You can think of it like that. If the DNA code in your body were unwound, it would stretch 600 million miles more than 6 times the distance between the sun and the earth. So it's an incredible amount of information. And then lastly, you have lipids, which are fats that don't dissolve in water. They're important for storing energy, and they make waxes and steroids for producing hormones. And a lot of our cell membranes are made of these fats. And finally, we have the law of conservation of matter. So this is a super important law of science that I want you to know, which is that whenever a matter undergoes a physical or chemical change, no atoms are created or destroyed. So you can see this. If something burns, you have the ash and the smoke, but nothing changed. You didn't add any or lose any of the atoms. They just changed. Okay, so you can see that here. They're both on the scale. We can change elements and compounds from one physical or chemical form to another, but we cannot, however, create or destroy any of the atoms involved in the physical or chemical change. All we can do is rearrange atoms, ions, or molecules into different spatial patterns with physical changes or chemical combinations. So that's a chemical change. All right, here's your checkpoint for understanding. So explain the relationship between elements and compounds, and explain how the law of conservation of matter applies to trees burned in a forest fire. All right, good luck.